Scientists have confirmed the discovery of an element that, by every normal measure of reality, should never have had time to exist at all. An atom with 117 protons crammed into a nucleus so heavy and so unstable that the moment it forms, it begins tearing itself apart. These atoms didn't last seconds. They didn't last even a full second. Most vanished in less time than it takes your eye to register a single frame of light. And yet, after more than 5 years of the most rigorous scientific scrutiny, the world's official bodies have accepted that these fleeting, almost impossible atoms were real. How do you prove something existed when every trace of it disappears before any human sense or conventional instrument can catch it? That question sat at the center of one of the longest and most painstaking confirmation processes in modern nuclear science. The real tension isn't just that the element is heavy, it's that creating it required racing against time itself. At Oak Ridge National Laboratory in Tennessee, scientists spent 250 days inside the high-flux isotope reactor building up just 22 milligrams of berkelium-249. That material has a half-life of only 327 days. Once it was made, every hour counted. The berkelium was purified over 90 days at the Radiochemical Engineering Development Center, then shipped on June 15, 2009, to the Joint Institute for Nuclear Research in Dubna, Russia. There, at the Research Institute for Atomic Reactors in Dmitrovgrad, it was turned into an ultra-thin target layer on titanium foil. On July 28, 2009, that target went into one of the world's most powerful heavy ion accelerators. For the next 150 days, a beam of calcium-48 ions, 7 trillion of them every single second, slammed into the berkelium. Most collisions did nothing useful, but under extremely rare conditions, the nuclei fused. The result was 6 atoms of element 117. 5 atoms of the isotope with mass 293 and 1 atom of mass 294. On April 9, 2010, the international team published those results in physical review letters. 6 atoms. That was the entire visible evidence. But 6 atoms detected in one laboratory, no matter how precisely measured, did not automatically rewrite the periodic table. Nuclear science has strict rules for claiming a new element. Independent confirmation is required. Other teams, using different equipment and different methods, have to see the same thing. Without that, the discovery stays provisional. So while the 2010 paper created excitement, the real scientific work was only beginning. The atoms had already vanished. All that remained were the recorded patterns of what they left behind. How do you confirm the existence of matter that existed for only tens of milliseconds? The answer lay in the decay chains. Each Tennessine atom didn't simply disappear. It transformed in a very specific way. It emitted alpha particles carrying exact amounts of energy, turning first into moscovium, element 115, then continuing through a precise sequence of further alpha decays down the periodic table until it reached known elements and eventually underwent spontaneous fission. These chains acted like unique fingerprints. The energies and timing of each step had to match theoretical predictions exactly. In the original experiment, the observed half-lives were actually longer than many models had predicted. Roughly 21 milliseconds for the 293 isotope and around 51 milliseconds for the 294 isotope. That extra stability was intriguing. It suggested the team might be edging closer to a region physicists have long theorized about. The island of stability, where certain combinations of protons and neutrons could produce elements that last far longer than the milliseconds seen here. But intriguing hints are not proof. More data was needed. In 2012, the Dubna team repeated the experiment and produced 7 additional atoms, strengthening the original observations. Then, in 2014, a major independent confirmation came from the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany. A large international collaboration of 72 scientists from 16 institutions, using berkelium targets again supplied by Oak Ridge, created new events that reproduce the same decay patterns. Only after these multiple, independent lines of evidence were carefully reviewed did the official recognition arrive. On December 30, 2015, the Joint Working Party of the International Union of Pure and Applied Chemistry and the International Union of Pure and Applied Physics announced that the criteria for discovery had been met. The priority for the discovery of element 117 was assigned to the Russian-American collaboration involving the Joint Institute for Nuclear Research, Lawrence Livermore National Laboratory, and Oak Ridge National Laboratory. In June 2016, the name Tennessine, symbol Ts, was proposed in honor of the Tennessee institutions that had produced the essential berkelium target material. The name became official in November 2016. This confirmation matters far beyond simply filling one more box on the periodic table. Tennessine sits in group 17 alongside fluorine, chlorine, bromine, iodine, and astatine. Yet because it is so heavy, its electrons move at relativistic speeds, a significant fraction of the speed of light. Those effects are predicted to alter its chemical behavior in ways no lighter halogen exhibits. If scientists could ever produce enough Tennessine to study its chemistry directly, it might behave more like a metal than like the reactive nonmetals we know. That possibility alone forces a rethinking of how we understand the periodic table at its farthest reaches. More importantly, these experiments test the fundamental forces that hold atomic nuclei together when electromagnetic repulsion between protons becomes almost overwhelming. The fact that 293Ts and 294Ts lived longer than some predictions is direct experimental support for the idea that shell effects and magic numbers of protons and neutrons can create pockets of extra stability. It is one small step toward the long-sought island of stability, where half-lives might stretch into seconds or minutes instead of milliseconds, finally allowing real chemical studies of these artificial elements. The work also carries implications beyond Earth. The same rapid neutron capture processes that labs are trying to mimic in miniature may occur in the most extreme astrophysical events, neutron star mergers and certain supernovae. By creating and studying these short-lived nuclei, scientists gain indirect insight into how the heaviest naturally occurring elements in the universe were forged. Tennessine is therefore both a laboratory achievement and a bridge to understanding cosmic nucleosynthesis. Every new confirmed super-heavy element tightens our models of nuclear structure and helps predict what might still be possible as accelerator technology improves. Yet even with Tennessine now officially recognized and named, the larger questions remain deliberately open. How much further can the periodic table be extended? Will future facilities using even more intense beams or different target projectile combinations finally reach the center of the island of stability? Or will there be a hard physical limit beyond which nuclei simply cannot hold together long enough to be identified? The 6 atoms created in 2009 and the additional events confirmed years later represent extraordinary human persistence. They also represent a boundary we are still exploring. We have proven we can force nature to create matter that does not exist on its own and capture its ghost before it vanishes. What we have not yet proven is how far that capability can ultimately go. Does the fact that humans can now manufacture elements that nature itself never assembled make you more confident in our scientific reach? Or does it leave you wondering how precisely tuned the rules of nuclear physics must be to allow even these brief moments of existence at all? If this story of 6 atoms, years of patient verification, and the official addition of Tennessine to the periodic table made you see the elements as something still unfinished and still full of surprises, share it with someone who thinks the periodic table is a closed book. The universe keeps giving us new pages to read, and we're only just learning how to turn them.